Hi everyone! Today I'll be covering the chain rule for partial derivatives. This is a useful technique for differentiating functions with one or more independent variables. So in Calc 1 and 2, we use the chain rule to differentiate composite functions like this. If you remember, if I was trying to find the derivative of f of g of x, that would be given by f prime of g of x times g prime of x. So hopefully that's familiar to you, but in Calc 3 we have a bit of a problem because now we're looking at functions of more than one independent variable. So we have to use the chain rule to be able to differentiate these. So in this case I have an f of xy, and we have practice with finding our f with respect to x and our f with respect to y, right, those partials. But this time x and y are differentiable functions of independent variable t. So this time, if I'm asked to find the derivative of f with respect to t, that equation is going to be given by the partial of f with respect to x times the dx over dt plus the partial of f with respect to y times dy over dt. And this is best visualized in a tree diagram. So say for instance we have our z is our f of xy. And because it has two independent variables, we're going to draw two branches extending from it for our variables x and y. And then because x and y both are functions of the independent variable t, we'll draw two more branches for t. Now as we go along the branches of our diagram, we're going to be taking the derivatives. So if I'm looking at the derivative of f, or z in this case, I have to take a partial derivative because it's split into these two x and y's, right? And so this would look like the partial of f with respect, well, I guess let's use z. So we have the partial of z with respect to x and the partial of z with respect to y. And then as I go along this upper branch, I have x and t, and because it's just one independent variable, I don't have to take a partial derivative, and I can just take dx over dt, and similarly down here I can take dy over dt. So now to find the equation for this chain rule, I am going to follow along the branches, and along the x branches I'm going to multiply the derivatives, so I get partial of z with respect to x times dx over dt. And same thing with y, I'm going to follow along the y branches, and I get the partial of z with respect to y times dy over dt. And then all I need to do is add these together, and I have that the derivative of f with respect to t is given by partial of z with respect to x times dx over dt plus partial of z with respect to y times dy over dt. So take a look at that, and hopefully it makes sense. A good example is for when you might see this is if you have something like f of xy, it's given by sine of 2x plus 3xy squared. But you're also given the x of t is 4t, and y of t is ln of t. So this is a case where if you're asked to find the derivative of f with respect to t, this is going to be the technique that you want to use. And notice that that extends for if we have two independent variables for x and y. So all this means is that when we're setting up our tree diagram, we have our z is equal to f of xy. We have our two independent variables, x and y. But each of these have two independent variables, as you can see here, u and v. So we have to extend the branches like this. And then as you're calculating your derivatives, you get your partial of z with respect to x and y, just like before. But this time, because x and y are functions of two independent variables, we have to take those partial derivatives as well. So we'd have partial of x with respect to u, partial of x with respect to v. Same thing with y, partial of y with respect to u, and partial of y with respect to v. So then if I'm asked to find, for example, the partial of z with respect to u, what I'm going to want to do for that is follow along all of the u branches. And same thing, I'm going to multiply along the x, so partial of z with respect to x times partial of x with respect to u, and then add what I multiply along the y, so partial of z with respect to y times partial of y with respect to u. And we do the same thing for v. If I was trying to find the partial of z with respect to v, I'm going to follow along the branches there, and that will be same deal, partial of z with respect to x times x with respect to v plus partial of z with respect to y times the partial of y with respect to v. This can be generalized for functions of multiple independent variables, and it might look complicated at first when it's set up in this format, but if you just draw the tree diagram, multiply it all out, it's the exact same thing, and it should make finding these derivatives a lot easier. So thanks for listening, guys. Here's the sources, and good luck.